Okay, so here we have Raoult's law. So the mole fraction of a component I in the liquid phase times the vapor pressure of it is equal to the mole fraction in the no, yeah, liquid phase, and then this is the vapor phase, mole fraction times the overall pressure. And um, so if we want to find the bubble pressure is just going to be, the bubble pressure is very easy. It's already in the equation, so it's just I equals 1 to n. It's the summation of is equal just to the overall pressure. So this is the bubble pressure. And what the bubble pressure is if you have all liquid and it's a mixture of two or more components, like in the case we're going to code is going to be benzene and toluene. It's the pressure that the first bubble will form at. You have a mixture of multiple liquids at, let's say, room temperature, and you want to make them boil. You'd have to essentially pull a vacuum on that and lower the pressure enough to where it'll boil, which is why water boils at much lower temperatures on Mount Everest. I don't know the exact temperature, but because it's so much higher up and there's less pressure than there is down at sea level. And we also have the bubble temperature. We get the temperature from the Antoine equation, or we can, but in the case we're going to be coding it, we're going to be doing a root. AI minus BI over T minus CI, T plus CI. So that'll be the Antoine equation, and that'll be essentially how you would get the temperature. But you'd solve it for a summation. And in our case, we're just going to be doing a root to find the bubble pressure. So we say give some desired pressure and then set the bubble temperature equal to that, and then find the temperature at that specific bubble pressure. It'll make more sense when I code this. And then we also have dew pressure, which is the opposite case of bubble pressure, where you have like all gas. It's like a gaseous mixture, and you want to start to condense that. What the dew pressure will be, first we got to modify Raoult's law. So we go, the mole fraction in the liquid phase is equal to the mole fraction in, and this will be the summation first of the uh, gaseous mole fraction times the overall pressure over the saturated pressure. Hi, Bella. And what we can do to solve this number, the mole fraction in liquid phase, is always going to be equal to 1. Okay, one quick correction. I think I said the mole fraction in the liquid phase is always equal to 1. It's the summation of all the mole fractions in the liquid phase that is equal to 1. So what we can do is just divide 1 by this summation, because this number right here, this is going to be a constant number, or it'll be our desired number, but we just do 1 over the sum of all the gaseous mole fractions over their vapor pressures is equal to the dew pressure. So this will just be BP, BT. That's not a PT, it's a BT. This will be our dew pressure. And then dew temperature is going to be this also from the Antoine equation, except that we're going to still do a root. What the dew pressure is if you have all of this, let's say we have gases at room temperature, or it's not, or no, we have gases at 100 degrees, so you'd have to start cooling that or start compressing it, either one or both, in order to get that to be liquid. And this is the pressure that the first bead of not water, first bead of liquid will form, and we'd have to determine the composition of that. If you wanted to determine the composition for either of these two instances where you were doing dew or bubble, you'd have to find modify it to be some. You'd have to modify it to be something. So like the gaseous mole fraction, you'd find it to be is equal to the I spelled that wrong. It'd be like the liquid mole fraction times the saturated vapor times the vapor pressure, just over the summation of all of the components. So that's how you'd find the mole fraction in the um, vapor phase. And if you wanted to do the mole fraction in liquid phase, is just this right here. Okay, that's the mole fraction in liquid phase. So that is how you solve for the bubble bubble pressure and temperature, and dew pressure and temperature. So
to start us off, first we've got like the wget, which is going to get all this chem tools, props, and whatever, like the properties. This is all the other stuff we've always used. CHE is just a way to get this. And in this case, we're just going to be using the properties of benzene and toluene. Bubble T, or bubble pressure list rather, because this is going to be the easiest one. And this is going to be with respect to liquid, because it starts as liquid, and with a constant temperature, return the sum of our x times our vapor pressure, and that is the bubble pressure. And down here we can go make subplots, and we're going to have one row and two columns. First, what we need to do is make an x-axis, which will be, we're just going to call it z1 for just a random thing. Z1 is equal to 0 to 1 with 11 spacings, so numpy linspace 0 to 11, no, 0 to 1 with 11. Oh, not linspace. And then we make a z2 for our component 2, which is going to be equal to 1 minus z1, because you have to, it's going to be the inverse because it's a binary thing. There's only two components, so they have to equal 1, so that makes this a little bit easier. And then we have a temperature is equal to, I think it should be 393.15 kelvins. And then we have our saturated pressure is equal to our vapor pressure. And then we have our bubble pressure list is equal to Z1 times P PSAT, and we just want the first thing because we only want benzene for this one, and then it's plus PSAT. No, it's Z2 times PSAT 2, or PSAT, well, the second one. So we have that, and then we can do figure dot add scatter. X is equal to Z1, Y is equal to BP list. Let's just see if this one works. Yep, we got that so far. And we're just gonna name this one bubble pressure. Okay, let's see, maybe it's just this. Maybe it's just single quotes. Sometimes it doesn't like bubble. Double. What? Name doesn't seem to want to work. Oh, wait. Column equals 1. Okay, well I've set that row in column 1, but it should be named bubble pressure. Maybe when I add the other ones it'll do it. Otherwise I'll have to figure this one out the second time. But then we can just have our bubble temperature. Did I put BP? No, I meant BP here. Bubble temperature in terms of X and P. And this one we actually have to make another equation because we want this to be a root. So this is just a vector. Temperature is equal to first term of the vector. We want this to return our bubble P minus pressure, and it's bubble P of xt, and then we just want this to return root of the equation with 298 as the gas. We want just the first, we want just this x term, so dot x to rip this x away. We just want the first x, so there. And if I'm going to, let's just add scatter because it takes forever. X is equal to z, y is equal to, nope, I've got to make some sort of list for this first. Otherwise it's not going to work. Okay, so actually what I've got to do first before I can start trying to graph this is I've got to make a bubble pressure, or I've got to make a bubble temperature list. Before I can do that, I have to set up some things. So first I've got to set a pressure equal to 150,000 pascals. I just have to make a, I'll just do this for now. Okay, and then to start this, I've got to do a for loop. So for x1, y1, for x1, y1 in range z1, hang on, I gotta look up how to do the range again. Or maybe I don't even need range, I just like to do range. So for this and that, our x2, y2, so our, this will be the then for the second compound in, I don't feel like, okay, well I guess that's where it is supposed to be. So x2, y2 is equal to 1 minus x1, y1, and then we just want to append, maybe it's, I think it might be these, it's either this or something started by, so bubble list append, and then we've got to have our bt, and then set this as a numpy array of x1, y1, x2, y2, and comma pressure. So let's see if that, nope. Function. I hate parentheses and brackets. These are supposed to not be brackets because I can never remember. Maybe I just need parentheses around this as well. Oh. Okay. Oh. Apparently I just had to run my stuff. Okay, so now I can just make this my BT list and then set this equal to row 1, column 2, and then name it bubble temperature. Oh. Yeah, okay. So that works. So there's our bubble temperature and bubble pressure. And what I like to do, this I found this quite easy. I just copy this and I can paste it. Control P. And I can just change this to my dew pressure. And it's literally just 1 over this, and not x. In this case, it's y, and then it's also in terms of yt because it's a gas going to a liquid. So there I have that. And then it's just a little more complicated to get this thing graphed, but I'm going to go ahead and start it. You know, and I could just do this. Because that's what I'm going to need. And then I'll eventually make a dew point list. And then that's dew point list is going to be in, or yeah, dew point pressure, I should say. That's going to be row 1, column 1. Yeah, I know it doesn't exist. Okay, so I already know what I'm going to name it. Yeah, I know it's non-existent, but I'm about to change that. It's an extra step, and to do it, I'm just gonna don't mess this up. And to do it, I'm just gonna go dp list is equal to just this in general. So I have that set up. I'm gonna just keep these all together for y1 because this is gonna be y in range. No, in z1, mole fraction in the vapor phase is equal to, for this, at least the second one, is equal to 1 minus y2, 1 minus y1. And then it's going to be do, well, that's fun. This is the downside to being in a school. You can still see the screen well, but you can't see me well, and I don't think we want that. So dew point list dot append, and I figured out from my last failure that I just need it to be this, no, and have it dp of an array. And then it's y1 and y2, comma, temperature, because I believe that should be it. No, that is, hang on, I messed this up. I'll figure that out in a sec. I can just power forward and get this all at least mapped out, and then all that's left to do is change this to dt y and then dp. It's pretty much, it's all the same because they're one and the same. It's just going to be the opposite. And then go, I guess this one is what I wanted to copy. And then go dt list, no, dt lit. Oh, I'm pressing Control D. DT list, and then make it do temperature. But first, what I need to do is just add a do DT list, and then essentially copy this. But go, and then change this to a Shift D. Just change that. Looks like I got the Okay, maybe it's not as simple as doing what I did with the copy paste, but let's see. Okay, so looking at my equations, it's actually y over BWF. So I got that one wrong. So I would change this. And then hopefully that means that I got... Yeah, okay. So that was the problem. Apparently it was not multiplication. Okay, so that is the plot of, for at least this binary vapor-liquid equilibrium thing. Um, I can beautify this up as well further by updating the layout. And let me check how to do this. Tick vowels equal, and then it's numpy linspace 0 to 1 with 11 data points. Apparently it also wants a title. Oh, it's update x-axis. Screw you, numpy. Okay, so I beautified it a little bit more so it's like you can see, and then in class we essentially calculated, I think it was 0.3. So I beautified it then further by giving it a title and its tick vowels, and it's actually update x-axis, not update layout total. So I just slightly beautified that. I could further beautify it, but I'll do that in the next video.